Welcome to day 3 of Master AI in 30 days. Yesterday, we conquered the mathematical foundations that power AI. Today, we're going to see those mathematical concepts in action as we explore machine learning essentials. Machine learning is where the rubber meets the road. It's the practical application of everything we learned about vectors, matrices, probabilities, and gradients. Today, you'll understand how AI systems actually learn from data, how we train them, how we evaluate them, and how we make them better. By the end of today's session, you'll understand the difference between supervised and unsupervised learning. You'll know what overfitting is and why it matters. You'll understand key evaluation metrics. You'll grasp regularization, feature engineering, and model selection. These are the practical tools that separate amateur AI practitioners from professionals. Machine learning is a discipline that combines mathematics with practical engineering. It's both art and science. The science comes from the math, but the art comes from experience and intuition. Today, we're going to develop both. Let's begin. Here's exactly what we'll accomplish today, and I want to be crystal clear about our learning goals. First, we'll understand two fundamental learning paradigms: supervised learning, where we have labeled data and the model learns the input output mapping, and unsupervised learning, where the data is unlabeled and the model discovers hidden patterns. These two approaches solve different types of problems, and knowing which to use is crucial. Second, we'll master the distinction between training and testing data. This might sound simple, but it's absolutely critical. Many beginners make the mistake of evaluating models on the same data they trained on, which leads to false confidence in model performance. We'll learn why this matters and how to do it correctly. Third, we'll learn to prevent overfitting, arguably the most common problem in machine learning. A model that memorizes training data instead of learning generalizable patterns is useless in the real world. We'll understand what causes overfitting and multiple strategies to prevent it. Fourth, we'll explore feature engineering and model selection. Raw data is rarely in the form that machine learning algorithms prefer. Feature engineering transforms data to make it more useful. Model selection means choosing the right algorithm for your specific problem. Finally, we'll touch on ensemble methods, combining multiple models to achieve better results than any single model. After today, you'll have the foundational knowledge to build real machine learning systems that work in the real world, not just on training data. Let me define machine learning clearly so we're all on the same page. Machine learning is the field of study that gives computers the ability to learn from data and improve their performance on a task without being explicitly programmed for every scenario. Think about traditional programming. You write explicit rules. If the email contains certain keywords, mark it as spam. If the temperature is below 5, turn on heating. Every rule is hard-coded. This approach works for simple, well-defined problems, but breaks down when rules become complex or when the environment changes. Machine learning is different. Instead of writing explicit rules, we provide examples, lots of them. We show the system thousands of emails labeled as spam or not spam. We show it images labeled as cat, dog, bird. We show it past transactions labeled as fraudulent or legitimate. The system learns patterns from these examples and can then apply those patterns to new unseen data. Here's the magic. We don't explicitly tell the system what patterns to look for. It discovers them itself. A spam detection system might discover that certain word combinations, sender addresses, and formatting characteristics correlate with spam. A cat detector might discover that certain combinations of edges, textures, and shapes indicate a cat. The system finds these patterns automatically through mathematical optimization. All of this is enabled by the math we learned yesterday: vectors representing data, matrices transforming information, dot products measuring similarity, and gradients enabling learning. Machine learning is the practical application of that math to real-world problems. Let's quickly define machine learning so we're all aligned. Machine learning is about giving computers the ability to learn patterns from data and improve at a task without us manually writing every rule. In traditional programming, we hard code logic. For example, if the email has certain keywords, mark it as spam, or if the temperature is below 5, turn on heating. This works for simple, stable problems, but it struggles when things get messy or constantly change. Machine learning takes a different approach. Instead of writing rules, we give the system examples, thousands of labeled emails, images, or transactions. From these, The model learns the underlying patterns and applies that learning to new, unseen data. Supervised learning is the most straightforward and widely used type of machine learning. Here's how it works. You have data where each example comes with a label, the correct answer. For spam detection, emails labeled as spam or not spam. For image classification, images labeled as cat, dog, or bird. For house price prediction, house features paired with their actual selling prices. For medical diagnosis, patient symptoms paired with confirmed diagnoses. In each case, you have input data and the corresponding correct output. The model's job is to learn the relationship between inputs and outputs. During training, we show the model thousands of examples. The model makes predictions, calculates how wrong it was using the math from yesterday, remember our error surfaces and gradients, and adjusts its weights to improve. This process repeats millions of times until the model achieves good performance. Once trained, you can give the model new emails, new images, new houses, new patients, examples it has never seen before, and it makes predictions based on what it learned during training. Supervised learning tasks typically fall into two categories. Classification is predicting categories spam or not spam, cat or dog or bird. Regression is predicting continuous values, house prices, temperature tomorrow, stock prices. Why is it called supervised? Because a supervisor, a human or system, provides the correct answers during training. This is powerful because it gives the model clear targets to learn towards, but it requires labeled data, which can be expensive and time consuming to create at scale. Unsupervised learning is fundamentally different. Here, you have data but no labels. No one has told the system the right answers. The model's job is to find structure, patterns, or relationships within the data itself. Imagine you have customer purchase histories, thousands of people and what they bought, but no one has labeled them as likely to buy online, price sensitive, or premium customer. Unsupervised learning can analyze these patterns and discover customer segments automatically. Maybe it finds that some customers consistently buy premium products, others hunt for discounts, others are seasonal buyers. These patterns emerge from the data without explicit labels. Another example is anomaly detection. Credit card companies use unsupervised learning to detect fraudulent transactions. Normal transaction patterns look a certain way. Consistent locations, amounts, frequencies, merchants. Fraudulent transactions deviate from this pattern. The system learns what normal looks like, then flags anything significantly different as anomalous. No one labeled transactions as fraud. The algorithm discovered it through pattern analysis. Dimensionality reduction is another unsupervised task. Imagine you have customer data with 100 features: age, location, income, purchase history, browsing history, and so on. Many of these features might be redundant or correlated. Unsupervised learning can compress this to 10 essential features that capture most of the variation. This is useful for visualization and computational efficiency. Why is it called unsupervised? Because there's no supervisor providing correct answers. The model must be clever enough to discover meaningful patterns on its own. This is both a strength, you don't need labeled data, and a challenge. It's harder to know if the discovered patterns are actually meaningful. This is absolutely fundamental, and I cannot stress its importance enough. Here's a critical mistake many beginners make. They train a model on a dataset, then evaluate it on the same dataset. The results look fantastic. Then they deploy to production, and the model performs terribly. What happened? The model memorized the training data. Imagine studying for an exam by memorizing the exact practice problems, then being given different problems on the actual exam. You'd fail. The same principle applies to machine learning. Here's the correct approach. Take your dataset and split it. Maybe you have 1,000 examples. Use 700 for training and 300 for testing. Never show the testing data to the model during training. The model sees only the 700 training examples. It learns patterns from these. After training is complete, you evaluate it on the 300 testing examples, data the model has never seen. Why does this matter? Because training performance is often misleadingly good. With enough capacity, a model can memorize training data perfectly. But if it's just memorizing, it hasn't learned generalizable patterns, so it will perform poorly on new data. Testing on held out data gives you an honest assessment of how the model will perform in the real world. There's actually a more sophisticated version of this called cross-validation, which we'll discuss later. But the principle remains, always evaluate on data the model hasn't trained on. This separation between training and testing is what separates careful machine learning from careless machine learning. Let's talk about two opposite problems that plague machine learning: overfitting and underfitting. These are like Goldilocks problems. You want the solution that's just right. Overfitting occurs when your model is too complex or trains too long. It fits the training data perfectly, even fitting the noise and randomness in the training set. Imagine a curve that wiggled and twisted to pass through every single training point. It would fit training data perfectly, but it wouldn't capture the underlying pattern. When tested on new data, it performs terribly because it learned quirks specific to training data, not generalizable patterns. How do you recognize overfitting? Training accuracy is very high, but testing accuracy is much lower. That gap between training and testing performance is the red flag. The model looks brilliant on training data and terrible on test data. This tells you it's memorizing rather than learning. Underfitting is the opposite problem. Your model is too simple or undertrained. It doesn't have enough capacity to learn the underlying patterns. A linear model trying to fit a curved relationship will underfit. It won't fit the training data well and won't perform well on test data either. With underfitting, both training and testing accuracy are poor because the model hasn't learned enough. The goal is the sweet spot in between. You want a model that's complex enough to capture real patterns but not so complex that it memorizes noise. You want a training and test performance that are both good and close to each other. Achieving this sweet spot requires techniques like regularization, which we'll discuss next, and careful choice of model complexity. Accuracy is not enough. Let me illustrate with an example. Suppose you're building a model to detect a rare disease that affects 1% of the population. A naive model that predicts no disease for everyone would be 99% accurate. But it's useless. It catches zero actual cases. This shows why accuracy alone is misleading, especially with imbalanced datasets. Precision and recall are more nuanced. Let's say your model predicts whether someone has the disease. Precision asks, of all the people I predicted have the disease, how many actually do? High precision means when your model says someone is sick, they probably are. Recall asks, of all the people who actually have the disease, how many did I catch? High recall means you're catching most of the sick people. These are trade-offs. If you set your threshold very high, only predict disease when you're extremely confident. You'll have high precision but low recall. You miss many cases. If you set it very low, predict disease easily, you'll catch more cases but have many false alarms, low precision. F1 score combines precision and recall into a single metric. It's the harmonic mean which penalizes extreme trade-offs. If either precision or recall is very low, F1 is low. This is useful when you care about both catching cases and avoiding false alarms. The key insight: choose your evaluation metric based on what matters for your problem. For spam detection, missing some spam might be acceptable, but false positives are annoying. Prioritize precision. For disease detection, missing cases is dangerous, but false alarms lead to confirmatory tests. Prioritize recall. For hiring decisions, you might want balanced precision and recall. Know your problem, choose your metric accordingly. Regularization is our tool for fighting overfitting. The core idea is simple: penalize complex models. If a model uses very large weights, weights that make wild predictions, we add a penalty to the loss function. This encourages the model to find simpler solutions that still fit the data. L1 regularization, also called lasso, adds a penalty proportional to the absolute value of weights. This has an interesting effect. It drives some weights all the way to zero, effectively removing features. This is called sparsity. Some features become irrelevant. It's useful when you want to understand which features matter most. L2 regularization, also called ridge, adds a penalty proportional to the square of weights. This discourages very large weights but doesn't zero them out. The solution tends to be smoother and more stable. This is more commonly used because extreme values in weights often indicate overfitting. Dropout is a clever technique specifically for neural networks. During training, randomly deactivate some neurons. Set their output to zero. This percentage might be 20% or 50%. It forces the network to learn redundant representations because it can't rely on specific neurons always being present. This prevents co-adaptation, where neurons become overly specialized to training data. Early stopping is conceptually simple but effective. Monitor performance on a validation set while training. When test performance stops improving or starts getting worse, stop training. You're preventing the model from memorizing training data by stopping before it can overfit too badly. All these techniques share the philosophy. Prevent the model from becoming too specialized to training data. They make training less efficient in the short term but produce models that generalize better. Feature engineering is often where the real work happens in machine learning projects. Raw data is rarely in the perfect form for machine learning algorithms. Feature engineering is about transforming raw data into features that make the model's job easier and its performance better. Normalization is crucial. Suppose you have features with wildly different scales. Someone's age in years, 0 to 100, and their income in dollars, 0 to 1 million. When algorithms compute distances or gradients, the income feature dominates because its numbers are much larger. Normalization rescales features to comparable ranges, often 0 to 1 or negative 1 to 1. This ensures all features contribute equally to the learning process. Encoding converts categorical variables to numerical form. Models work with numbers, not categories. If you have a feature color with values red, green, blue, you can't feed these strings directly to a neural network. You might encode this as three binary features. Is red 0 or 1? Is green 0 or 1? Is blue 0 or 1? This is called one-hot encoding. Feature selection means choosing which features to include. You might have 100 features, but only 10 are actually predictive. Including irrelevant features adds noise and complexity. Good feature selection improves model performance and reduces overfitting. You can use statistical tests, correlation analysis, or machine learning algorithms to identify important features. Feature creation means combining or transforming existing features to capture patterns better. If you have month and day features, creating a is weekend feature might be more informative. If you have latitude and longitude, creating distance from city center might be more useful. This requires domain knowledge and creativity. The saying in machine learning is data and features matter more than algorithms. Two different teams, one with poor features and one with excellent features, will see dramatic differences in results even using the same algorithm. Invest time in understanding your data and engineering good features. Choosing the right algorithm for your problem is crucial. Different algorithms have different strengths, weaknesses, and requirements. Let me walk you through some common choices. Decision trees are like flowcharts. They make a series of yes-no decisions to reach a prediction. They're interpretable. You can trace exactly why the model made a decision, and they handle categorical and numerical data well. However, individual trees tend to overfit, which is why we often use them in ensembles. Support vector machines, SVMs, are powerful classifiers. They find an optimal boundary between classes in a high-dimensional space. They work well for both linear and non-linear problems when you use appropriate kernels. However, they can be slow on large datasets and require careful hyperparameter tuning. Random forests solve the overfitting problem of individual trees by combining many trees. Each tree trains on a random sample of data and features. The final prediction is the majority vote across all trees. Random forests are robust, handle many feature types, and rarely overfit badly. They're often a great first choice for tabular data. Neural networks are the most flexible. With the right architecture and training, they can learn almost any pattern. They excel on high-dimensional data like images and text. However, they require lots of data, significant computational resources, and careful tuning. They're also less interpretable than trees. It's harder to understand why they made a specific prediction. Model selection isn't about finding the one best algorithm. It's about matching algorithms to problems. Start with simple models like linear regression or decision trees, then move to more complex models if needed. Remember the principle of Occam's razor. Simpler models that perform well are preferable to complex models, all else being equal. Hyperparameters are settings you choose before training. They're different from weights and biases, which the model learns during training. Learning these hyperparameters well separates good practitioners from great ones. Common hyperparameters include learning rate, how much to adjust weights at each step during gradient descent. Too high and training becomes unstable and diverges. Too low and training is glacially slow. Finding the right learning rate is crucial. Model architecture hyperparameters include the number of layers in a neural network, the number of nodes per layer, the depth of decision trees. Regularization strength controls how much we penalize complex models. Batch size controls how many examples to process together before updating weights. Grid search is straightforward. You specify ranges for hyperparameters and try all combinations. If you have learning rate in 0.001, 0.01, 0.1, and regularization in 0.1, 1, 10, you try all 9 combinations. It's exhaustive and finds the best in the search space, but becomes computationally expensive with many hyperparameters. Random search randomly samples combinations instead of trying all. Surprisingly, this is often more efficient than grid search, especially when you have many hyperparameters. It's statistically more likely to find good regions of the hyperparameter space than systematically testing all combinations. Bayesian optimization is more sophisticated. It uses machine learning itself to model how hyperparameters affect performance, then intelligently selects which combinations to try next. Based on past results, it guides the search toward promising regions. This is the most efficient but also most complex approach. Hyperparameter tuning often takes more time than training individual models. It's a necessary investment for production quality models. Cross-validation is a more sophisticated approach to evaluation than simple train-test split. It provides more reliable estimates of model performance and makes better use of available data. Here's how k-fold cross-validation works. You divide your data into k equal sized chunks called folds. Maybe k equals 5, so you have 5 folds. Training happens 5 times. Each iteration, one fold serves as the test set, and the remaining 4 folds serve as training data. You train, evaluate, record the result, then move to the next fold as test set. Repeat until every fold has been the test set exactly once. At the end, you have K performance measurements. Maybe your accuracies were 0.92, 0.89, 0.91, 0.90, 0.93 across the 5 folds. You can report the average, 0.91, and standard deviation as a measure of stability. Cross-validation gives you not just a single performance number, but a distribution showing how consistently the model performs across different data samples. Why is this better than a single train test split? First, you use all data for both training and testing, which is more efficient. Second, you get a distribution of scores showing model stability. A model that gets 0.95 on one split and 0.50 on another is unstable. It's probably overfitting. A model that consistently gets 0.85 is more trustworthy. Third, your performance estimate is less dependent on lucky or unlucky splits. The trade-off is computation. You train k times instead of once. For k equals 5, that's 5 times the training time. But for reliable model evaluation, it's worth it. Cross-validation is standard practice in professional machine learning. Ensemble methods combine multiple models to achieve better performance than any single model. The philosophy is that diverse models combined intelligently are better than any individual model. This works because models make different types of errors, and combining them averages out these differences. Bagging, bootstrap aggregating, works by training multiple models on random samples of the training data. Each model trains on a different random subset. When making predictions, all models vote or average their outputs. Random forests are bagging with decision trees. The diversity comes from different training samples. Bagging reduces variance. Individual models might be unstable, but their average is more stable. Boosting trains models sequentially. The first model trains normally. Then you look at its errors, which examples it got wrong. The next model trains on data, where those misclassified examples get higher weight. The second model focuses on correcting the first model's mistakes. This continues for many iterations. Each model is weak individually, but together they're strong. Gradient boosting is a powerful variant that uses gradient descent to optimize the combination. Stacking uses a meta model to learn how to combine predictions. You train multiple base models, get their predictions, then train a meta model on these predictions to learn optimal weights. It's more complex, but can achieve excellent results. Why do ensembles work? Suppose you have 10 models, each 70% accurate. If their errors are independent, the ensemble of their majority votes is far more accurate. The more diverse the models, different algorithms, different hyperparameters, different features, the better the ensemble. Ensembles are powerful but come with computational cost. You're training and storing multiple models. But for performance critical applications where accuracy matters most, ensembles are worth the investment. Tomorrow is day 4, Deep Learning Fundamentals. We're going to shift from traditional machine learning algorithms to deep neural networks, which have revolutionized AI over the past decade. We'll go deep into neural network architecture, understanding exactly how layers, neurons, and weights combine to create powerful models. We'll explore how to train neural networks effectively, understanding concepts like backpropagation, optimization algorithms, and activation functions. We'll study convolutional neural networks, the architecture that revolutionized computer vision. CNNs use convolutional layers to extract features from images in a way that preserves spatial information. They power image recognition, object detection, and image generation systems. We'll explore recurrent neural networks and their modern variants like LSTMs and GRUs. These networks process sequential data, time series, text, audio, where the order and temporal dependencies matter. They power language models, machine translation, speech recognition. We'll discuss transfer learning, a powerful technique where you take models trained on massive data sets and adapt them to your specific task. This is how many modern AI systems work. You don't have to train from scratch with billions of examples. You leverage pre-trained models. Finally, we'll explore real-world applications. How does ChatGPT work? How does Stable Diffusion generate images? How do self-driving cars see? These aren't magical. They're applications of deep learning principles we'll explore tomorrow. Excellent work today. You now understand machine learning essentials. See you tomorrow for deep learning.